Today's topic is tangent graphs. All right, we'll get started. The next thing that I'm going to be talking about is introducing the new tangent graph. Now in this, I've got a really good Desmos demonstration that works for this, and it works great in the classroom. Not sure how well it will work here because it doesn't quite update as frequently. You're not getting every single frame of my video that I'm showing you. But what I've got here, you should be able to see my iPad screen. I've got a slider. At the moment, I can just drag this thing around the circle, and I've got some other things that are hidden, but I can just put this anywhere I want. And it's changing in values of pi on 6, which you can't quite see because it's a massive decimal place. No, it's pi on 12. But I can set it there to be 2 pi, or I can set it there to be 3 pi. I can sort of change this anywhere. Now, if we want to graph the sine function, I can just press this button and sort of jump to here somewhere. Let's remind ourselves that the sine function is tracking the height above the line. So over on the circle on the left-hand side, you've got one yellow line that's going down from the x-axis. And the angle, as the angle increases, that's just changing our value on the x-axis. So on our circle, our dot that has now just hit 2 pi on that right-hand side, that shows that the sine curve is actually tracking the height of this point. So if I go another little bit further just to keep that on the line, we can see that the height of that line just above the x-axis symbol right over on that right-hand side is the same as the height at that point there, which is 2 pi plus pi on 3. So 7 pi on 3 gives us that sine value. So that's where the sine curve sort of comes from. It's one way to visualize it. As I said, this works a lot better when it's actually in the classroom, but we can see that mapping the height of that orange line as we go around the circle is a way of visualizing where that sine curve comes from. I'm going to do exactly the same with our cosine curve. And so if I turn on the cosine animation, we can see that we get something similar, except instead of tracking the height above the line, we've got a sort of 90-degree rotation where our green line is the distance from the y-axis. So it's a horizontal distance. We know that cosine is our horizontal distance, and that's one of the reasons that as we start it, our angle is 0, our distance from the y-axis is 1. So here's another example of why our cosine graph looks very similar as we go round. I can zoom out a little bit and you can see that it sort of just keeps on going all the way up to 4 pi for this. All right, so with that in mind, what on earth is a tan graph going to look like? I'm going to put that down. Let's reset that all the way to 0. You may remember that my definition of tan was if we draw a vertical line at if we draw a vertical line at x equals 1, which is very close to pi on 3, so it's just to the right of that pi on 3 dot. I'm sorry I can't annotate my screen or point to something, but I'm talking about that point there. Actually, I can even just get it to draw the line x equals 1. So if I just get it to draw the line x equals 1, that red line there is the tangent to the circle. And remember that as our angle gets up, we're going to think about where we might extend that line to hit the red line. Let's think about what's going to happen then. If I'm going to turn on my tangent animation, which is going to be blue, and if I go up there, there's a few things that's happening, and it's sort of hard to see. But what you'll see at this point is the angle, which is the blue dotted line, is extended towards that red line, and it hits at that right-hand purple dot. That's where our tangent is extended to. And then that's at an angle of pi on 4. So the other purple dot represents the point. I can actually show you here. The other purple dot represents the point, pi on 4, 1, which is the height of the tangent at that point. So if I now go just a little bit further, we can see that now that angle, oh, sorry, I meant to go to pi on 3, not pi on 12. So there we've got an angle that is pi on 3. We've got our dotted line that's going up to pi on 3. And we're extending that to our tangent line, and it's touching nearly at the right point. It's too confusing to talk about, so I'll keep on going from there. All right, so what we've got now is the shape of that tangent curve. You can see it sort of starts at about a 45-degree angle and then just keeps going up and up and up. What's our value at tangent? What's the value of tan pi on 2? Well, we know that tan pi on 2 is undefined, and so this has no value. But as we get really, really close to it, we're going to get something approaching infinity. Thus, this is a vertical asymptote. We've seen vertical asymptotes before in our function study unit. We haven't seen them in trig yet, but it's exactly the same as what a vertical asymptote in functions looks like. What happens to tan as we go over, as we tick over the pi on 2 value? Well, remember, you may remember that here when we're going underneath, we still extend that line back to x equals 1. And so our tan value becomes negative, and it just goes, again, gets slower and closer and back to 0 until we get back to here. Let me get it to right on pi. A bit fiddly. Not going to let me. There we go. All right. This thing here, I want to hide that x equals 1 line. Just to get. Let me hide my circle as well. This thing here is basically one period of our tan graph. Now that looks strange. We've got a vertical asymptote down the middle. So there is a vertical asymptote going straight down at x equals, not at 1 though. If we've got a line at x equals, what are you doing to me? We've got a line at x equals pi on 2. So this red line here is a vertical asymptote. If I zoom out, you can see we're never going to actually touch it. It gets closer and closer and closer to that asymptote, never gets there. And then we start from the other side coming negative. That's essentially as we're coming down the other side of our unit circle. When we get back to, let me put my circle back on. When we get back to pi, so we've come down the other side, we're at that left-hand edge of the circle, our tan value is 0, and we also flip back over to be positive again. And so as we go around the bottom side of the circle, as I increase my angle across the bottom side, I get exactly the same pattern again. So that's what 2 revolutions of our circle looks like. If I put the sine function back on there, you can see that that's normally what we consider the period of a trig graph. The period of a graph is 2 pi. However, period of the tan graph, we've actually gone through our cycle twice in that time. So one of the most important things that you're going to know about our tan graph if we're sketching y is equal to tan x, we have a period not of 2 pi, but of pi. So that's fundamentally different to, there's a whole bunch of things that are different about the tan graph, but one of the important ones is that the period is pi. Thus, if we've got something like y is equal to tan of nx, then our period, if we've got a dilation in here, our period is equal to pi on n, not 2 pi on n that we're used to with our sine graph. If I go back to Desmos, we can keep on going and we get a pattern that just sort of looks like that. Now, with our sine and our cosine graphs, the most important concepts were the period and the amplitude, and also where the max and the minimum. The period we've talked about, the period of this one is pi. Amplitude doesn't mean anything for tan graphs. It doesn't make sense to say that this has an amplitude of 1 or an amplitude of 2 or anything else. We can talk about the A value and we can talk about a dilation factor, but that's not the same as talking about the amplitude. So make sure you're never referring to the amplitude of a tan graph. We also don't have any maxima or minima. So there is no, I mean, that's one of the reasons there's no sense of the amplitude. But also the fact that there's no maxima and minima means that that's usually what we used to do for calculating our period. Our period was the distance between the maxima. Now the easiest way to think of the period is that it's the distance. Let me jump to here so we can talk about this and I can refer to what I'm actually pointing to. So if we're sketching a tan graph, we start here and just sort of let me put my normal pi and 2 pi. I'll go a little bit further. Yeah, sorry. Let's go a little bit further to 2 pi. Halfway there is there. So we're sketching our pi on 2 and our pi and 3 pi on 2. and 2 pi. And the first thing that I normally draw in, if it was a sine or a cos graph, I'd be putting in my maxima and my minima, but I don't do that anymore. The most important thing now are my asymptotes. And so let's identify that our standard tan graph, and this is going to change when we put some transformations in there, but our standard tan graph has an asymptote at pi on 2 and an asymptote at 3 pi on 2. And we like to label those VA at x equals pi on 2, VA at x equals 3 pi on 2. And then my graph starts in the middle, goes up like an asymptote, and then does that. This is what I consider one period, one cycle of the tan graph. Some people like to think it's the bit that goes between asymptote to asymptote. So you can sort of also think of that as one cycle of the tan graph. But if you do that, then you're going to start getting confused that that cycle doesn't start at 0. So it's easier to think of, and I know it sort of breaks your brain a little bit thinking that your cycle goes across an asymptote, but it's easier to think of that as one cycle of the tan graph, and then we can keep on going. That is another cycle of the tan graph. So we can get through 2 cycles in our normal 2 pi period. So the asymptotes are incredibly important when we're sketching a graph or when we're practicing the earlier skill that we did, which is going from a graph back to the function. The first step is, can we work out what the period is, and we can either do that from our asymptotes, or if we work out our period, that's going to tell us where our asymptotes are. So when there's a massive relationship here between the asymptotes and the period, just like previously with sine and cos, there's a big relationship between the period and the maximums, or the period and the minimums. All right. Let me also just show you quickly in Desmos. Let's create a new graph, and I just want to, no, I don't want to do that. New blank graph. Let's sketch tan x. Y is equal to tan x. That's what we get for. It's not going to let me. Here we go. I'll just change this step to be pi. All right, so that's sort of the tan graph that we're looking at. Let's think about what happens with our dilation factor. Well, first I'm going to put in a translation factor here of plus a. Let's think about what our a is going to do. And essentially this is our translation, which is going to go left and right, the same as we would normally expect. Sorry, I'm moving that too fast, and the frame rate of the Google Meet can't keep up. But if I just turn that a little bit, then as I increase this slider, we can see that it slides to the right a little bit. What's happening here is all our asymptotes are changing as well. So the easiest thing to do if you're sketching a graph, I'm going to do this in more detail when I have more time, but that won't be until next term. We're going to look at sketching tan graphs in more detail, but working out where your asymptote is based on where this translation factor is, translation amount is, and then from there working out all your other asymptotes. That explanation of tan graphs, let me also, I haven't quite finished this. Taken a bit longer than I wanted to, but that's okay. We're about to finish. What happens if this is a dilation factor? A dilation factor, this is our horizontal dilation factor. And so we can see that essentially that jams our asymptotes in tighter. So that makes a lot of sense. But again, we can see that these AX plus B, if we've got our general form of AX plus B, we're going to, that A and B values in there, except I'm going to, let me change A to be N just so that we're more consistent with what I've been referring to previously. So N and X are going to change my asymptotes quite significantly, but our dilation vertically, our A value, isn't going to change our asymptotes at all. It's hard to see in that diagram, in that demonstration there, but our asymptotes aren't really changing if I've got A. I'm really not happy with this Desmos frame rate thing. I can't really explain the concepts that I want to, but we are going to be looking at tan graphs in much more detail later on. To start with, I am going to set some exercises. I know it's to the end of the lesson, but I do want you to, and you've only got 2 minutes left, but I do want you to just practice something which you can work on this afternoon or sometime at your leisure over the holidays. So I am going to set some exercises that I would like you to do based on what we've done so far. I hope that's okay. I'm sorry. I'm sorry that I'm setting you holiday work and that I'm giving you things to catch up on our very last lesson on your very last period of the term. But based on just what we've talked about, you do have enough understanding to work on exercise 6J. We're going to sketch the graphs. Question 1 and question 2 are just on sketching really basic tan graphs like this one here. So I want you to do that without me formally teaching the sketching the tan graph process. And I also want you to have a look at question 4, which is not about sketching graphs, but it's asking you to solve tan equations. We haven't done much work on that, but you can see that if we've got some translation upwards, tan x plus pi on 4 plus 1, then finding our x-intercepts of this graph is going to rely on us. We're going to need to solve tan equations to do that. And so getting back into our skills for solving tan equations is there as well. So I'm going to stop talking now. That is the end of our lesson.